we have been discussing about the photochemistry of the reactions involving singlet oxygen to generate endoperoxide and so on. So the ozonide and cyclic peroxide have also been known to undergo cleavage to give to remove the oxygen part of the material, and then so ozonide and cyclic peroxides. Cyclic peroxides on photolysis undergo cleavage. On photolysis, to give carbonated product and oxygenated product. For example, if we have a system like this, you have a 4-membered ring, another 4-membered ring, right? And this is a cyclobutene, a dimethyl substitute is also a dimethyl. Then we have oxygen peroxide linkage, and then this is connected to ozonide, right? And the 2-methyl group. So if we have a system like this, we have this is oxygen, and then carbon, another carbon, and then on oxygen. So it is a ozonide, and then we have this on photolysis, H nu, undergo cleavage here as well as here, right? And then give rise to divar benzene. So this part is separated, and then it is a nothing but net. We have divar benzene, and other part is a anhydride. C double bond O, C double bond O, so 3 oxygen. So divar benzene and anhydride. So this is a photo exclusion reaction where the cleavage takes place to give this. Similarly, if we have a system like this, the cyclobutene right, and then we have again 2-methyl group is X actually. So we can have it is possible that if we have X being an alkyl group or an halide group, so we have an oxygen, endoperoxide, and then this is again ozonide. So this again under photolytic condition undergo photo exclusion reaction, a cleavage here to give rise to cyclobutadiene plus acetic anhydride anhydride. So we have anhydride reaction. So another interesting reaction of similar type is shown by giving rise to divar naphthalene. Divar naphthalene. Divar naphthalene can be prepared. Divar naphthalene can be prepared. Divar naphthalene can be prepared by photolysis of corresponding oozides. By photolysis of corresponding ozonide. And so if we have a naphthalene ozonide, this is one benzene ring, this is another benzene ring, this is C6H5, and then we have a 6-membered oxygen containing this is endoperoxide. So if we have, so this is the corresponding the ozonide derivative. This on photolysis can undergo as usual a cleavage here, give rise to divar naphthalene. Plus acetic anhydride CH3, C double bond O, C double bond O, CH3 anhydride. Stick anhydride. So now this is this what we have seen. We can see that the ozonide under photolytic condition cleaves in such a way that two oxygen are forming two carbonyl, and one is the anhydride oxygen. And then there is a separation of the carbocyclic system, and all the oxygen containing compounds are separated in another form. So this is a very good reaction for the synthesis of divar naphthalene, divar benzene, and also this is here X being, this is valid for X being CH3 as well as Cl, chloro. When this X being chloro also, if the oxygen, the X being chloride group also works in the similar fashion. Now we have already seen that the epoxides, opens up, opening of epoxides under photolysis under photolytic condition epoxides opening of epoxy under photolytic condition. So if we have already seen one example with tetraphenyl group. So if we have a system like this, CN and pH, this under photolytic condition, although it gives rise to, opens up to give a deuterionic intermediate, C double bond plus, and then this CN pH, negative charge here, and then we have a H and pH. So this is what we have seen last time. With tetraphenyl epoxide opens up in this way to a deuterionic intermediate. So here also when we have a cyano substituents or deuterionic intermediate, deuterionic intermediate is formed. And then this on we also saw that this on further photolysis generates the a carbonyl compound and the what we call it as a carbene. So we get C double bond O pH H plus this part goes as a carbene plus CN pH. So this carbene derivative can be generated on photolysis of epoxide opening to give a zirconic intermediate, and then which further on photolysis gives carbene as intermediate. Similar opening has also been found in nitrogen in similar reaction is observed in nitrogen containing heterocycle. In nitrogen containing heterocycles, that is aziridines. We just mentioned this last time, but now we'll see in more detail how aziridine can be, opening of aziridine can be exploited in further reaction of this zirconic intermediate. Aziridine. So if we have a system like this, so let's see, if we have a system like this, C double bond N, a 3-membered ring is a pH here, and then the 2-methyl group, this is aziridine. And then if you have a, and then this on photolysis, can undergo ring opening as usual to give a pH C triple bond N minus, and then you have a positive. So it is a this zirconic intermediate is similar zirconic intermediate is formed in the case of nitrogen containing heterocycle like aziridine, as we have seen in the opening of the epoxide. So here also aziridine opens up to give a zirconic intermediate, and this has been reported to add in a 3+2 fashion. So it reacts with CO2 to give a 5-membered ring system. So CO2 can add C double bond O double bond O. So this is going to add in such a way 3+2. So this is attacking here and then is attacking here. So what we end up with a product like this, C double bond N. Right. So this is the product which is formed. So it is a nice trapping of the zirconic intermediate, which is formed by the opening of the aziridine ring. So we can see that the aziridine under photolysis opens up to give a dipolar species, which adds to carbon dioxide, and then to give rise to a this heterocyclic system. Heterocyclic. So it's a nice way to synthesize nitrogen and oxygen containing heterocycle. Not only this has also been found to add with an alkene, say X being a substituent. So it acts in a similar fashion. So for example, you have a double bond here. So in the same way, it can add. This can add to, and then this will add to this. So again, it's going to form a 5-membered ring. X here, phenyl group is phenyl, is R here, phenyl here. Is a phenyl group. So you can see it is possible to synthesize the cyclic heterocyclic system on a reaction of the zwitonic intermediate or dipolar species, which is from on opening of aziridine on photolysis. So aziridine nitrogen containing heterocycles on photolysis opens up, give rise to a dipolar species. This is the evidence of existence of this dipolar species is well established by trapping of these dipolar species, trapping with CO2 to give this cyclic product, or trapping with the alkene to give this cycle. So formation of these products will very well explain, suggest the given evidence that the reactions, the aziridine on photolysis opens up to give this step. So the cyclopropane opening, the opening of the cyclopropyl ketone have also been reported. Photolysis of cyclopropyl ketone has also been reported, and one example is here. You have a double bond, and then you have a carbonyl, you have an R here, and then you have two substituents here and the phenyl. So this system on photolysis opens up in this to give rise to a diaradical species, right? This is pH. And then we have a carbonyl R, right? So the cyclopropene carbonyl on photolysis opens up to a diradical species, 1,3 diradical. Radical 1,3 diradicals can further can lead to can give rise to a ketene, a carbene intermediate, carbene intermediate, and this carbene intermediate undergo 1,2 shift, 1,2 shift, to give a ketene as intermediate. Okay, just a moment. You have a double bond, you have a R is coming here, R is coming here, then we have a, so this ketene intermediate. So you can see a very interesting transformation has been observed in this. If we have a system like this, cyclopropyl ketone, cyclopropyl ketone on photolysis gives 1,2 diradical intermediate, and this 1,2 diradical is transformed to a carbene intermediate, undergo 1,2 shift to give a ketene intermediate, and we know that this ketene in the presence of solvents, is a protection like methanol, gives rise to ester. So give C double bond O, R, C double bond O, OCH3. So the formation of this ester is really a very good evidence of opening of the cyclopropanyl ring system, and then which is going under photolytic condition, going to a diradical species, to a carbene intermediate, and then to a ketene intermediate, and then the formation of an ester leads to give this product as one of the products. Similarly, the opening, this is a cyclopropyl. So if the cyclopropyl is a part of an oxygen, like the oxirane, opening of oxirane is much faster. Instead of cyclopropane, if it is an oxygen containing 3-membered ring, the opening of oxirane, means oxygen containing 3-membered ring, is much faster. And if we have a system like this, say for example, we have a cyclopentanone, and then we have an epoxide and the 6-membered ring. So this is again very similar to the earlier one, cyclopropanyl ketone. Here we have an epoxy ketone, and then this undergoes essentially it involves beta cleavage. Under photolytic condition, it undergoes beta cleavage. Beta cleavage here also under photolytic condition. Under photolytic condition undergo beta cleavage. So this is alpha bond, this is a beta bond. So this carbon oxygen bond is cleaved. So this is beta bond. So there is a cleavage of this, giving rise to a diradical species like this, C double bond O. We have a oxygen, a 6-membered ring, a diradical species like this, and then this undergo 1,2 shift. So same as this before. So 1,2 shift. Here also it undergoes 1,2 shift. So we have this diradical, and then there is a the shift of this. So this is a very interesting product where we have a cyclo, right? You have now you can see this is a linkage. This is a spirotype compound. This comes and attach here, and there is a ketone. So this is a very nice product which is formed by epoxy ketone involving beta cleavage under photolysis. So another example of epimerization of epoxide, epimerization of epoxide under photolytic condition. Of epoxide has also been reported if we have a system like this. So this is a 6-membered ring. It is a carbonyl here. The carbonyl here, the epoxide. So you have a 3-membered ring. So this on photolysis, as usual, undergo beta cleavage. Is alpha, is beta. Undergo beta cleavage to give diradical species. Beta cleavage to give a diradical species, right? Oxygen, a diradical. Now there is a now it is a the cyclic system has now opens up. Now the free rotation is possible, and it is all it is a reversible reaction. Reversible reactions, because it's just a epimerization of methyl group here and methyl group here, the carbonyl here. and then we have a oxygen. So you can see the so this epoxide has undergone epimerization through uh, beta cleavage under photolithography to give an opening of this isopropyl group, and then to this. Another interesting reaction has been observed in cyclohexenone. Interesting reaction, cyclohexenone. Interesting reaction observed in cyclohexanone epoxide. Cyclohexanone epoxide involving similar involving epoxide involving similar type of cleavage. So we have a system like this: cyclohexanone, C double bond O, cyclohexanone. We have an epoxide here, and then you have a you have a phenyl group. The phenyl group is again cyclohexenone epoxide, pH. So this is again is all reversible. Under thermal it goes back. So under photolytic condition is involving the is opening of the epoxide. So we get a so you have a double bond here, you have a double bond here, O minus, a dipolar species. pH, a dipolar species. Dipolar species is formed in cyclohexanone epoxide on photolithography, and then this acts as a diene, acts as a diene and can react with uh, uh, the cyclo this furan, and then it's going to add in its fashion, giving rise to a, so it is a reaction taking place on one of this. So like this. So what we get, the final product which is formed after the addition across this dipolar species is this one, C double bond O, pH. We have a pH here, and then we have right. So you can see this is a very good trapping product which is formed. On reaction of cyclohexanone epoxide. So under photolithography, opening of cyclohexanone, and then to dipolar species which reacts with this the furan derivative in a fashion 3+2 cycloaddition reaction to give this type of products. So we have a very interesting reactions we have seen to this reaction.